Hello guys, welcome to my YouTube channel for the big structural hub. So today I want to tackle a question from past paper. This is structures 1, Knec October, November 2020. So the question reads, it's question number 1A. Draw shear force and the bending moment diagram for the beam loaded as shown in the figure 1, indicating values at critical points. 17 marks. B. Determine the point of contraflecture, if any, for the beam in 1A. So this is the beam. You are supposed to draw the shear force and the bending moment diagram and then determine the point of contraflecture from either side. So the first thing to do, as usual, extend this line to give you space to draw shear force and the bending moment diagrams, and make sure you are doing it on one page. So like that. Like that. After doing so, the next thing to do is to calculate the reaction. And to calculate the reaction, we will use the equation of equilibrium, because this is a single span overhanging beam. As you see, it is overhanging on the right hand side. So solution. Let's some moment about any point. Let's say summation of moment at A should give you 0. So the next thing we'll be calculating is reaction at F. So reaction at F is moving in anti-clockwise direction in reference to point A. So we have minus RF minus RF times the distance from A to F. 1.5 plus 1.5, that is 3, plus 2, that is 5, plus 1.5, that is 6.5, plus 1, that is 7.5. So times 7.5, like that. Close the bracket. A force which is so close to A, we have 20 kilonewton in which direction? This direction. So that is clockwise, plus 20 times 1.5, like that. Any other force close to A, we have a UDL of 15 kilonewton per meter. In which direction? So it begins from C and it ends at D. So this direction, that is clockwise. So it will be plus 15 times 2. We are changing our UDL to a point load. So 15 times 2, and then times the bending moment for UDL, it acts at the center. So that is 2 over 2 plus the distance from where we are assuming our moment from. So that is 1.5 plus 1.5, that is 3. So plus 3. like that. And then we have again a point load of 25 kilonewton for a concentrated load in each direction. If you are air, so it's moving in a clockwise direction in reference to point A. So that is a positive bending moment. So that is 25 times the distance from A to E. So that is 1.3 plus 1.5, that is 3. 3 plus 2, that is 5. 5 plus 1.5, that is 6.5 times 6.5. Close the bracket, times 6.5. The final force or the final loading is 12 kilonewton. In which direction? Again, from this to this. See my movement of my teaching aids. So like that. So that is clockwise direction. So it's a plus 10 times the distance from A to here. 1.5 plus 1.5, that is 3 plus 2, 5 plus 1.5, 6.5, 6.5, 7.5, 8.5 times. Is there any other force? No, equals to 0. After doing so, you can now simplify by opening the brackets. So negative 7.5 RF plus this one, this. If you multiply, you will get 30 plus here 1, here 1. So 1 plus 3, that is 4. 4 times 30, that is 120. Again, 25 times 6.5. 25 times 6.5. 162.5 plus 162.5. 12.5 times 8.5. 12 times 8.5. That is 102 plus 102 should give you 0. Go ahead further and carry out the operation. So that is 30 plus 120 plus 162.5 plus 102. You get 404.5. So minus 7.5 RF should give you 404.14.5. No, plus should give you 0. So like that. So with this one, negative 7.5 decreases to other side, it changes from negative to positive. So 7.5 RF should give you 0.5 over 7.5, which implies RF equals to, so you divide 414.5 by 7.5. That is 55.27. 55.27 kilonewton. So that is RF. Again, to find A, we will use one of the equation of equilibrium, which says that summation of upward forces should give you summation of downward forces. So we have RA plus RB should give you 20 plus 15 times 2 plus 30 plus 25 plus 12. Already we have RB, so RA plus 55.27 should give you, so 20 plus 30, that is 50, 50 plus 25, that is 75, 75 plus 12, 87, so that is 87, so which imply RA equals to 87 minus 55.27. So RA will be 87 minus 55.27. So that is 31.73. 31.73 kilonewton. After doing so, now you can be comfortably draw your shear force diagram. So draw a baseline. So this is shear force diagram. Shear force diagram. Again, we begin plotting or drawing our shear force diagram. Reaction at A is 31.73, so approximate is positive. So that one, let's say there, give it a value, that 1.73. It will be constant up to the next force for the next loading. So take that 1.73 minus 20. You get 11.73. So 11.73. So somewhere like there. So it will be again constant up to the next loading. So that is 11.73. So 11.73. Like that. It seems my pens are not writing. Yes, like that. And then 11.73 minus IUDL, which is 15, converted to a point load, that is 30, minus 30, you get 18.27. So 18.27 is around somewhere there, so 18.27. So draw a diagonal line, cause it is IUDL, like that. And then it will be constant up to 25 kilonewton. Again, take negative 18.27 minus 25. 43.27. It will be 43.27. 43 somewhere like there. So 43.27. Again, it will be constant up to reaction F. plus, take negative 43.27 plus reaction at F. Reaction at F is 55. 55.27. That is 12. So you get 12. So this is 12. And then it will be constant up to 12 again. So 12 minus 12 is 0. So it goes back to 0. This is now your shear force diagram. So this is plus, plus, minus, minus, plus. Like that. Then the next thing is to calculate the bending moment values. Let me create a space for bending moment values. So bending bending moment at A equals to 0 equals to bending moment at G. Bending moment at B it will be, we are now here, bending moment at B, it will be the area of this shear force diagram. So that is a rectangular shape. So it will be length times width. So that is 31.73 times 1.5. So that is, let me punch my calculator, 31.73 times 1.5. That is 47.6 kilonewton meter. Then after that, let's now go to point C. Bending moment at C. It will be bending moment at B plus the area of this part. So that is a rectangle, a rectangular shape. So plus 11.73 times 2.0. So this one will be 7.6 plus 11.73 times 2, that is 23.26. 23.26. So this one will be plus 7.671. Yes, 71.06 kilonewton meter. Again, bending moment at C, it will be 47.6 plus the area of this, that is 11.73 times 1.5. So this one will be 65.20. 65.20 kilonewton meter. Yes. Then bending moment at this point, let's say this is point Y. So for you to get bending moment at point Y, you need to get this distance. Let's say this is X, and this is 2 minus X. So you will be required to calculate this distance X, because it will help you to find the bending moment at Y, which will be the maximum bending moment along the beam. So let's use the similar triangle rules. So it will be X over 11.73 should give you 2 minus X over 18.27. If you carry out your operation very correctly, you will find that, which implies X equals to 0.82 meters. So kindly carry out the operation for this so that you can find this value 0.82. So here we have 0.82, and then here it will be 1.18 meter. So bending moment at Y will be bending moment at C, which is 65.20 plus a half times 11.73 times 0.82. So this one will be 70.0. So equals to 70.0 kilonewton meter. Bending moment at D bending moment at B. At B will be 70 minus a half times 1.18 times 18.27. So this one will give you this one will give you 59.23 kilonewton meter. Bending moment at E. Bending moment at E will be bending moment at B, which is 59.23 minus this area, so that is 18.27 times 1.5. So this one will give you 31.82 kilonewton meter. So bending moment at F. So bending moment at F will be bending moment at E, which is 31.82 minus 43.27 times 1. So this one will give you negative 11.45 kilonewton meter. Negative 11.45 kilonewton meter. So that is it. You can now draw our bending moment diagram. So bending moment diagram. Bending moment diagram. At A is 0, at G is 0. So let's go to at B. At B is 47.6 at B, 47. At B is 47. But 7.6. So this one will be a diagonal line like that. And then at C you have 65.2. At C 65.2. Again keep the diagonal. 5.2. And then at y is 70, the maximum. At y is 70. So this one will be a smooth curve. Opposite side here. And then at D is 59. At D is 59. Again a smooth curve. Again at E is that one. At E is that one. That 1.82. So this one will be a straight line, not a straight, a diagonal line. Like that. And then at F is negative 11. At F is negative 11. So it's 11. So it's a diagonal line. And then 0. So this is positive, negative. Like that. So this is question. We have solved question 1A. 1B, point of contraflection. Point of contraflection or point of inflection. So let's now solve this. The point of contraflection is where a bending moment changes sign from negative to positive or from positive to negative. And as you can see from the diagram, this is the point. So this is the point. Let's give it distance C from the right hand side. So here we have a reaction, and then here we have of kilonewton, that is G, and this is RF. And then let's give it Z, point of contraflection. So let's get distance C. So we have this Z, B, point of contraflecture from right side of the beam. So if you can draw, you can take this one and then draw here. So this is Z, RF, 12 kilonewton. So this distance 1 meter. This is C minus 1. So bending moment at Z equals to 12 times C, which direction are you moving in reference to point Z? So this way, that is clockwise, minus RF times C minus 10. Because this one is moving and clockwise direction, and the distance is C minus 10, like that. So 12 C minus RF C minus 10 should give you 0, because bending moment at point of contraflecture is 0. 12 C minus 55.27 into bracket C minus 1 should give you 0. C minus 55.27 plus 55.27 should give you 0. Minus which imply C equals to 1.28 meters. So point of contraflecture is 1.28 meters from right side of the beam. And the question ends there.